Now moving to what A-level doesn't do. With A-level, you talk about hydrogen spectra, you talk about absorption spectra, in which an electron moves from one energy level to a higher energy level and absorbs photons of light in order to help it do that. You talk much more about emission spectra, in which you have excited electrons. You passed electricity through hydrogen or whatever it might be. The electrons are in higher energy levels and they decay or they relax down to lower energy levels, giving off a photon of light. Now I'm going to leave much of that conceptual illustration until we start working through the A-level questions workshops, but what I do want to do is take it that little step further and actually calculate the numbers that you have associated with either these absorptions or emissions. So this first one, we're looking at a photon absorbed when the hydrogen atom, so therefore it's going to go from a lower to a higher energy level, undergoes a transition from n equals 2, so that means we're talking about the Balmer series, up to n equals 4. Now, the equation that we have associated for all of these is the frequency or the energy, or 1 over the wavelength, depending upon which value of a constant you use. But the thing that's the same from all of those, whether you're getting energy, frequency, or 1 over wavelength, is you take the two energy levels concerned, N1 and N2, and the difference between them in terms of energy or frequency or 1 over wavelength is simply 1 over N1 squared minus 1 over N2 squared. So therefore, whether you're calculating the energy or the frequency or 1 over the wavelength depends on not what the values of N are, in this case 2 to 4, but what the value is of the constant you use. Now, many times the constant that's given is the one associated with energy. Sometimes the one you're given is the one associated with 1 over meters. In this case, I'm going to use the one that has frequency in it, and I can tell s to the minus 1 seconds to the minus 1 tells me this is the frequency. So to get the frequency, all I have to do is pop in the various values. Frequency is the constant, 3.29 times 10 to the 15 per second, 1 over n1 squared minus 1 over n2 squared. I will always put the smaller energy level first. That guarantees I get a positive number out of this, and we had a discussion on that in the movies, if you remember. Can't go wrong putting the smaller number first here and then think about the answer you get. So we've gone from 2 to 4, so 1 over 2 squared minus 1 over 4 squared. Pop all that in and we get that the frequency 6.17 times 10 to the 14 per second. This makes sense. It's a positive number. All frequencies should be positive numbers, and it's in that sort of same ballpark. Hopefully you've done enough problems by now that you know that the frequencies associated with all of these spectra up there 10 to the 13, 14, 15 type size. Next one, calculate the wavelength that a photon emitted. So now we're going from a higher transition 5 down to 3, talking about an emission spectrum. Last question, of course, talked about an absorption spectrum. Now we're going to again use the same wonderful equation, but now look at the value that I'm given of R, 1.096776 times 10 to the 7 per meter. So in other words, if I use this constant that I'm given, then what I'm going to calculate is 1 over the wavelength, because you can see it's 1 over meters. So let's pop all that in, see what we get. 1 over wavelength is 1.09676 times 1 over 3 squared minus 1 over 5 squared. Again, I'm putting this smaller number there first to guarantee that this gives me a positive number. Punch that in on the calculator. 1 over lambda is 7.7993 times 10 to the 7 per meter, which is 1.282 times 10 to the minus 6 meters. Okay, now the answer there, it's not in meters, right? It's going to be in nanometers, and times 10 to the 6 meters is 1,000 nanometers. So 1.282 times 10 to the minus 6 meters, 1,282 nanometers. I'm not going to focus on that conversion here. I already did that on a previous page. What I'm going to do, though, is address something that oftentimes confuses students, I believe, unnecessarily. Let's say that the only value of the constant that I knew was the one for frequency. Well, let me do that calculation then. Frequency is The new constant that I'm going to use, right, 3.9 times 10 to the 15 per second, but it's still, this important bit stays the same, 1 over n1 squared minus 1 over n2 squared. So the frequency of this photon would be 2.3 times 10 to the 14 per second. Well, of course, we know how to go from frequency to wavelength. We just talked about that on the previous set of slides. So all we have to do is use the relationship that C is lambda times the frequency, pop that in, and if you did that, you would find out that indeed you got the same value, lambda 1.282 times 10 to the minus 6 meters. Okay, some calculations that are relatively straightforward to do when you're just asked for the frequency or the wavelength. What you've got to do is not allow yourself to be confused by the various, can we calculate energy here? Can we calculate frequency here? Can we calculate 1 over wavelength? You just change the constants, but the important bit, the crucial bit, the 1 over n1 squared minus 1 over n2 squared stays the same. Now, possibly the nastier type of calculation here is illustrated with this one. A hydrogen atom in its ground state, so n equals 1, absorbs a photon of wavelength, that's the wavelength. To what level does it move? And here I'm giving you the constant that is associated with 1 over wavelength, seeing as how I'm giving you the wavelength. So again, we're going to use this same equation. 1 over n1 squared minus 1 over n2 squared times a particular constant. Seeing as how the constant we're given is 1 over wavelength, let's say that this will be 1 over wavelength. And of course, we're told the wavelength, 97.2 nanometers. Okay, and as I said, ground state, so the first level, n1, is equal to 1. Well, lambda is 97.2 nanometers, but we don't want nanometers, we want meters. So we'll just replace that by 97.2, nano of course being times 10 to the minus 9. Pop that in everywhere, 1 over that wavelength equals 1 over, or the nice little constant, 1.096776 times 10 to the 7 per meter, 1 over 1 squared, and then of course we don't know that final energy level, so we'll call that x. Divide, or generally get this whole thing together. Okay, so we leave that alone. We'll divide both sides by 1.096776 times 10 to the 7, and that all together gives us 0.938. So rearrange a bit, so 1 over x squared over the other side minus 0.938 from both sides. So we get 1 over x squared is 1 minus 0.938, so 0.062. Flip that, so x squared is 1 over this, which is 16. X therefore equals 4. So photon of wavelength, 97.2 nanometers, is just the right amount of energy needed to pop an electron from the first to the fourth energy levels.